Hello and welcome back to NES Emulator hacking. Today we are going to pick up where we left off in the previous episode. And if you didn't see the previous episode or the previous video, then what we were doing there was basically implementing the ability to track cycles correctly when a memory access crossed a page. And it turned out to be quite an interesting problem to solve. That seems to now be in place. I did hear in the comments from that video that I wrongly used the term cycle accuracy. In fact, what was done was just the standard thing you have to do for tracking cycles if you want to have any hope of emulating any games on the NES properly. And cycle accuracy is actually a much more specific and difficult thing to do, which is when you properly emulate the cycles of the CPU inside the 6502 in a very low-level emulation way, so that you actually create the correct. You actually sort of fully simulate the processor, as it were, and that's not what we're doing now, and it's not what we're going to do because it's not required, although it does make for a better emulator generally. But there's a big trade-off in performance. Okay, so what are we actually going to do today? I'm sort of not sure. What I want to actually tackle is beginning to look at the memory map of the NES. So the memory space of the NES is not only RAM, it's of course many other devices connected to a common bus, and those devices are given some of the address space. This is what's called memory mapped I/O, and those devices are interesting things like the pixel processing unit of the NES and the audio hardware and a bunch of other stuff. And so that's what I want to take a look at today, and just begin to implement some of that hardware and some of the logic behind that. So the idea with memory mapped I/O is that actually it's a lot like reading and writing from memory, but you can actually sort of toggle the settings of different hardware. And the way this is normally done is with things called registers. It's a little bit different from like a CPU register. It's like a memory address that you write to, and that has some internal function. All common microcontrollers these days also have this. You have memory mapped registers. Okay, so that's what we're going to do. We're going to take a look at them, and I'll say up front, I don't really know what we're going to find. I think it will be something that we can tackle, but I don't know what we're going to find, and I think it's just going to be an interesting journey. Most of what we're going to be doing is just finding out the information, finding out how the console works. Again, I'm not an expert, so if I just say anything wrong, correct me. I'm also not a C++ expert, so if I do anything weird in C++, let me know as well. I'm super happy to learn from people who know more than me. Okay, so let's dive in. I think the most interesting place to start is the NES Dev Wiki, which we looked at last time. And basically, if we go here to the NES reference guide, we'll find a bunch of stuff here. So we've got articles about the CPU, the APU, which is the audio processing unit. We have the PPU, the pixel processing unit, input devices. Input devices are also memory mapped. So to check if the up button or the left button is pressed, that you actually read from a segment of memory. You can't write to that segment of memory, but you can read from it, and you can find out if a button is pressed. And there was no fancy, analog sticks or anything back in the NES days, so there's no. It's literally if there's a 1, then the button is down, and if it's a 0, this might be flipped. I don't think they are, but sometimes you get this flipped active low kind of thing. We'll find that out anyway. And of course, there are other things that get connected to the bus, like the stuff that's inside the NES cartridge, the RAM and the ROM, and the sort of the way in which those interfaces are connected into the memory. Those are also memory mapped. And often, if you wanted to have a game that had a lot of graphical assets or a lot of logic or a lot of sound, it takes up a lot of space, and you might have actually needed more than the address space could allow, more than the sort of RAM or the ROM allowed in the address space. And so things called mappers were actually used. I think this is what mappers are anyway. Of course, I'm in the way. NES games come in cartridges, and inside of those cartridges are various circuits and hardware. Different games can use different circuits and hardware, and the configuration and capabilities of such cartridges is commonly called their mapper. Mappers are designed to extend the system and bypass its limitations, such as adding RAM to the cartridge or even extra sound channels. More commonly though, mappers are designed to allow games larger than 40K to be made. So yeah, indeed, with a mapper, could actually be a physical chip inside the cartridge, which RAM or ROM, or maybe both, were connected to, and by sort of writing to memory mapped I/O, the memory mapper would sort of present to the console as a piece of memory, and by sort of controlling that through memory mapped I/O, you could actually sort of switch in different memory banks, and that will allow you to extend the space. So that's interesting in and of itself. The CPU also has, if we look here for the registers, this is going to be the standard set of registers, which are already implemented. Memory map. Okay, so this is a good start. So everything from, and these are all hex, of course, these numbers are all in hexadecimal. So everything from 0 up until 7FF, which is 800 hex bytes, is 2 kilobytes of internal RAM. So that's actual RAM. If you write to that, you can use that, I think. I think that's accessible to everyone. Oh yeah, of course it is, because it's on the 0 page. So it's, writing to this first 256 bytes, there are a bunch of special instruction addressing modes, and we covered that in the previous episode. I'm actually going to slip my gloves on because it is freezing in this room, and last time it was very cold. Alright, so, and then we have 3 mirrors of that address space, and that's actually quite interesting in and of itself. That's one of the first things we can implement, because it's pretty straightforward, but it's also kind of an interesting, weird thing. And there's reasons that these mirrors exist, and maybe I'm not the best person to explain it, but if you check out Retro Game Mechanics Explains channel, they have a series all about the SNES, the Super Nintendo, which was the console I grew up with, actually. I didn't have a NES growing up. But the SNES, it has this same mirroring behavior depending on more circumstances. But it's very interesting to see why. And I really recommend you check out some of their videos if you find that interesting. Okay, next we have 8 PPU registers. That's something we're going to look at, because that's also going to be really interesting to see. Because they're going to have a specific behavior, and of course we're not going to be able to implement the entire PPU today. By the way, there was a comment in the someone in the previous video was surprised that we weren't able to implement shocked. I don't know, but the entire emulator was not implemented in one video. That won't be the case. I think it takes a very long time, but hopefully we can cover some of the most interesting parts in these videos. All right, and then we've got a bunch of we've got a mirror of the PPU registers that repeat every 8 bytes. That's pretty interesting. And then from 4000 until 4017, we have APU, so the audio processing unit, and the I/O registers. It's also going to be something interesting to look at. audio is something that really the audio synthesis stuff is something that really scares me, and I don't really understand how it works at the moment. And I'm sure it's actually something that can be tackled and is not too difficult. But in another series that I make on this channel, which is all about was all about building a virtual machine, is now about turning that virtual machine into a fantasy game console like the NES. In that I've sort of just omitted audio as a feature, and maybe I'll get there with it one day, but I've sort of skipped over it now. But unfortunately can't do that in the NES, although I may come to that later. And then we have APO and IO functionality that is normally disabled, see CPU test mode. We'll take a look at that. And then everything else is cartridge space. So that's going to be down to how the cartridge itself maps its devices to the bus. C note. We'll take a look at that note. I assume this is the note, or is this just general explanation? I'm not sure. Okay, so some parts of the 2 kilobytes, I think this is pronounced, of internal RAM from 0 up until 7FF have predefined purposes dictated by the 6502 architecture. The 0 page and the stack always uses some part of this range. Yeah, of course. So I think we mentioned that in the previous episode as well, right? That the stack is always on this 1 page. Games may divide up the rest, however the programmer deems useful. See sample RAM map for an example allocation strategy for this RAM. We'll take a look at that. Note, here's the note. Most common boards and the INES mappers address ROM and save work RAM in this format. I feel like I couldn't pass that sentence. Most common boards and INES mappers address ROM and save/work RAM in this format. Okay, so then for the majority of time, for everything from 6000 up until 7FFF is battery-backed save or work RAM. So it's sort of like SRAM, which has a battery attached. So when you turn the console off, your save game doesn't go away. I think for the NES, that wasn't that heavily used. It's quite an expense to add to your manufacturing costs back in those days. And that's why a lot of games had passwords, because passwords were a much cheaper way of allowing a user to keep progress without actually having to shell out for the extra cost of a battery. Alright, and then we've got everything from 8000 up until FFFF is just usual ROM, commonly with memory with mapper registers, see MMC1 and UX-ROM for examples. It's quite interesting here. You have to sort of be able to detect in a given game, and I think that comes in the ROM format itself. You have to be able to detect which mapper is being used and sort of respond accordingly. And if you don't implement a mapper that was used, then you're not going to be able to play that game. It's just so simple. The CPU expects interrupt vectors in a fixed place at the end of cartridge space. So, that's interesting. So the interrupt vectors are at the very, very end of the... And if you don't know what an interrupt vector is, an interrupt vector is basically... it's like a table of addresses that live in memory. And when the CPU is interrupted, either by a software interrupt request, or by external hardware, like there was a physical pin on the CPU, which if it got an electrically high or low signal, it would be considered to be interrupted, and it would look at this table and jump to a certain address, and it would set some flags, and you would have a block of code, well, you will have a block of code that just does something during this interrupt request. And then at the end, instead of a return from subroutine instruction, like a regular return instruction, so pop stuff off the stack and jump back, you'd have a return from interrupt. And I think the main difference there is that the NES or the 6502 will automatically push some of the registers onto the stack when an interrupt occurs. I think that's the case. We'll find out. But in any case, the NMI vector, so that's the non-maskable interrupt vector, which is the address, is going to be at FFFA, and will take up 2 bytes, 60-bit address space, of course. Then you have the reset vector, so basically either when the machine is powered on or when some sort of software-triggered reset occurs. That's what's happened when you press the reset button. Did the NES have a reset button? I'm actually not sure. And then there is the RLQ/break. So interrupt request, which is a software. No, that's not true. Is there a software interrupt in the 6502? I don't remember implementing an interrupt request instruction, so maybe there are no software interrupts, but there are often software interrupts in CPUs. Okay, but the break vector, so there is a break instruction. So for debugging purposes, you can stick a break instruction in and expect that your code will jump to this, whatever is at this address. Okay, so if a mapper doesn't fix the NMI, well, actually the whole thing here, if it doesn't fix it to some known bank, typically along with the rest of the bank containing them, of course, because this is in cartridge space, right? So the cartridge is, of course, defining where these things are going to happen. That's like a programmer responsibility. Yeah, so basically what it's saying here is that if your memory mapping hardware is allowing for more space than just, you don't just have one ROM bank. If you've got more than that and you're swapping them out using the memory mapper, writing to memory mapped registers, then you need to sort of store your interrupt request at the end of all of the ROM banks, because if you swap it out and then an interrupt comes in, and by its nature you don't know when an interrupt is coming in, right? That's why you're being interrupted. Then it was just going to jump to some garbage address, and that's not what you want. So you have to put it at the end. So this is more of a developer message actually than it is a emulation message. Okay, that's interesting. Let's start out with the mirrors of the 2 kilobytes. Kibibytes. I should check what how that's pronounced. People get really pedantic about that. Yeah, so let's start out with the mirrors. That shouldn't be too difficult. Okay, so back in the code. Don't know if we looked at this last time, but I have here a bus header. I actually watched about half an hour of a video of someone implementing a NES, which is one of the other big series I think you'll find if you search NES Emulator C++. I believe it's one lone coder. And I copied his basic setup for the bus. But actually I stopped watching because I kind of felt like it was spoilers. And I wanted like the excitement and the stupid discoveries to be all of mine. So I've got a little base header, which is pretty much how he wrote it. And the very simple class outline. So basically now, if you write to the bus, and at the moment we only have the CPU, right? So the CPU, let's try and find somewhere where this happens. At the beginning of the step method of the CPU, a read is performed on the program counter. And some of these other instructions are performing writes. So decrement will cause a write to happen to memory. So we write to an address and we give it a value, or we read from an address. And in the CPU class, these two functions, they literally just, they basically delegate that read or write out to the bus. So yeah, we sort of dereference the bus pointer that we have and call a method on it. It's really that simple. It makes it a little bit easier that you don't see this all over the code and sort of unnecessary clutter everywhere. Okay, so then this is what we actually have. So basically what happens right now is it comes in, if we're going to do a write, and we're checking the address for some given range. And right now that range is literally the entire address space. If that range is if the address is anywhere in the address space, then actually just write to RAM. And RAM is defined here to just be a uint8 vector of this size, which is the full address space. I wonder if I should start adopting the more C++ style naming convention like this, but there are so few members in this class, and I don't think anyone is going to get confused by that. So for now I won't, but maybe I will refactor it later. Okay, so we need to start dividing this up, because it's no longer, just write freely into the RAM or read freely. Now we know, for example, that if we're writing in this range, then actually that's the first 2 kilobytes of internal RAM. So let's actually put that in. If we're writing to 0x07ff, I think I'm using lowercase, then that's just a piece of regular RAM. Let's write to it. All right. And then, actually, if we're could do this as like else ifs and stuff, but I don't think this is gonna be the source of performance problems. Okay, so if it's from address 0800 onwards up until FFF, then actually we're going to write back. And what's going to be the easiest way to do this? I think what we can do is oh wait, this actually goes up to 1FFF, of course, because this is covering the whole thing. So I think what we can do is we can mask off from the address this address basically. No, that's not true, but we can mask off 7FF, and that would give us in binary 0x7FF 07FF. So in binary that would give us this bit mask, which is, oh my gosh, 11 bits long. So the first, if we're writing to anywhere in the first 11 bits of the address, and we're in that range, we're just going to mask off those bits, because, well, let's just see that this should work. So if I end that with OX07FF, and that should give us the actual address that we want to write to, if we're anywhere in that range. We can test that out by coming into this test CPP file and deleting a bunch of stuff. And you can see what we have here is basically a bus is initialized, a CPU is initialized, a variable I here, which is used to just insert instructions into RAM in an easy way. And then we connect the two together. And so what we want to do now is basically we want to just read some values and check what comes out in RAM. So if I do b.write and we write to the address 0000 and we write the value, what's a simple easy value, AA. And then what we want to do is we want to see that was written correctly. So what I'm going to do is I'm going to print f, everything else other than print f. and we can write in here the address, so 0x0000, and what we found in there was %hx. I believe that will output in hexadecimal, and we'll just do it. We'll read it back from that address. So we'll b.read. Error type. That's strange. I think it's like, for some reason, when I opened up VS Code today, it sort of was having a bit of a difficult time with my header paths and everything, but it shouldn't. But and I'm not going to fix that now. So so we're going to read from there, and we'll see what comes out. So should just be able to run make. Oh, a bunch of nice warnings there, and it's to do with it's the warnings here are all to do with like switching between unsigned and signed integer for doing conversions, but that's actually what I want to do. So maybe there's a sort of more sophisticated way I can tell the compiler that no, really, this is what I'm trying to do. Oh, and a warning is generated, and then an LD warning, no option found for llib. But I think should still be okay. So in the bin output, the main, if we run that, we see AA. So that's pretty unexciting. So let's make it a tiny bit more exciting. Let's try to write to one of these addresses that we know would be mapped to another one. So we know, for example, that 800 is actually just going to mirror 0. So if I write here, well, let's do 2 reads. Let's like before we end off here, let's say 0800. That's going to be also %xh, and we'll do b.read from 0800. So then let's write into that. Now we can write bb, and we can actually just do the same read again. And you actually need to recompile. Bin main. So, oh, okay. So actually, it didn't seem to work. So that's an interesting thing. So what's going on here? So if the address is yeah, okay, we wrote the write code, but we didn't write the read code. that does help. Okay, so I'm just gonna copy paste this, get rid of that part, and we're going to do returns from here and not writes. And if anything is like given, which is outside of this range, we'll just return 0. So sort of, if anything goes wrong or doesn't appear to be running correctly, we'll return 0. I'll plug in my charger to make sure that it doesn't disappear. Okay, so now we're reading from those, and if we run that, yeah, nice. So we read here that A value is reflected in both places, and let's just check that it's reflected in all the places that it should be reflected. So it's not only 800, but it's also then at 1000 and 1800 hexadecimal. So 1000 and 1800, and it might just be worth putting some of this stuff on different lines. So 1000, 1800, and just write a second value somewhere else in that range, like we know, for instance, that everything up until so let's actually make a UN16T offset and just say we're going to offset ourselves hex 50 bytes. And just add the offset in all of these places instead of working out what the actual addresses would be. But yeah, that's sort of a more general way of doing it, right? If it's anywhere in this thing, we should see the right results. And yes, you can't leave trailing commas in C++. It is one of the very nice features, I think, of JavaScript, because it allows you to just copy a bunch of new items without having to worry. Yeah, I like trailing commas. And we're writing AA, so that's not, not that helpful, and also it didn't. Oh. Yeah, okay, so we know what these addresses are going to be, right? This is going to be 50. Not quite as general as I thought it was going to be. And let's write a different value instead. Let's write CC instead. Cool. So that's really quite straightforward. We've mirrored the memory in those 2 kilobyte ranges. So it doesn't matter where you read or write to, it's all going to work the same, except of course for the 0 page, which gets its own set of special instructions, and except of course for the stack. Although the stack is just regular memory, it just the stack pointer is moved around, so that should have no effect. All right, so we're up here in the memory map. That's some progress. And then we get the NES Ppu registers. Let's take a look at that. So these are going to be 8 registers that control some behavior of the pixel processing unit of the NES. Let's move myself out of the way. The PPU exposes 8 memory mapped registers to the CPU. These nominally sit at 2000 hex through 2007 in the CPU's address space, but because they're incompletely decoded, they're mirrored every 8 bytes from 2008 up until 3000 FFFF. So a write to 3456 is the same as a write to 2006. So it's going to be a little bit trickier to implement, but basically we'll be able to use somewhat of the same technique. All right, it's a nice amount of address space to just throw away on this mirroring as well. It's like, yeah, it's a lot. It's a lot of things you could do with that. A lot of like cartridge space you wouldn't have to have for extra ROMs. It would be very annoying if you were the developer of a game and you just needed just that extra bit of just that extra 1000 hex of address space, and you just couldn't have it. All right. Immediately after power-up, the PPU isn't necessarily in a usable state. The program needs to do a few things to get it going. See PPU power-up state and inner code. Okay, that's interesting. That's more for the developer again. And that's more something we would expect to see in a ROM when we load it up. So we can probably expect to see pretty much the same bring-up routine happening for any given game. All right, so let's get to these registers. What do we have? We've got Ppu Control. I assume that's for control. So this is showing the 8 bits of this register. I don't know why that thing is not going away. I can just put this back up here. Oh, that's better. So those 8 bits, these first 2 bits are grouped together. So we have 2 bits of like 4 possible values of information stored there. Then I stores some other piece of information. S is storing some piece of information. And then the same out here. So there's a bunch of flags basically. So what do we have? NMI enable, non-maskable interrupt. We have PPU master slave. Don't know exactly what that will do yet, but it's going to change who's in control of something. The sprite height, so that's a 1-bit value, 1-bit value, and I believe that in the NES, the way that sprites work is that they can be either 8 or 16 pixels high. Background tile select, sprite tile select, increment mode, and name table select. So I don't really know what those things are. I'm going to open up the Ppu Control page. Apparently I've opened it before, but I don't remember any of the details of that. Then we have the Ppu mask. So it's the color emphasis, the sprite enable, the background enable, sprite left column enable, background left column enable, and grayscale. Interesting. We'll see what those do. It looks like they control some kind of drawing functionality to do with color. Ppu status. 3 bits are used, the rest are unused. I wonder if you can write to those bits and store information in them. Okay, so with that we get v blank, sprite 0 hit, sprite overflow, and reads to reset write pair for 2005-2006. Okay, so that's these. Okay, so v blank, that's going to be a flag that tells the processor that it's in the v blank time, I assume. And I don't know if everyone here is familiar with the way that screens are drawn out or were drawn out in this time, but it's like highly related to the technology which was common in TVs, which is like line scanning, like with an electron beam. So basically, graphics are drawn line by line in the SNES. So we'll draw a line, and then it's going to come back and draw the next line and come back, and it's a physical beam, right? There's like electrons being fired out at a screen, and that's what creates the colors. Now, there is some time. There's like a time period, like before the line starts being scanned, after the line starts being scanned, and then right at the bottom when the whole screen has been drawn, there's something called the blanking time, the vertical blank. And that's a chunk of time where you can do some computation. And that's what VBlank is. And the reason it's important is because the CPU cannot access certain parts of memory during while the screen is being drawn, while the electron gun is passing through, right? Because of course, like you're going to get some really, really weird graphical effects if you just sort of leave that as a potential side effects, like really strange. So basically it's sort of like off limits to write to certain parts of memory before this happens. So that's why that will be important. Sprite 0 hit, I'm not exactly sure what that is. Seems that it might be something to do with collision. Sprite 0 is probably usually the player, so it might be some sort of hardware-based collision detection. Sprite overflow, I think that flag is set when there are too many sprites on a given line. So the NES also can only draw a certain number of sprites on any given line. I don't know what the limit is exactly, we'll find out. But as the beam is being scanned, I think basically when that line goes to be drawn, if it already gets to the point where it can't draw more sprites on that line, whatever the sprite was on the end basically doesn't get drawn. And the sprite overflow tells you that happened, I think. And then if you know that sprite overflow occurred, what you can actually do is you can shift some of your information about which sprite to draw. You can sort of use it like a cue, and you can move that sprite backwards and forwards in the table. And that means that on the next frame, even if sprite overflow does occur, you're actually going to draw the sprite that you didn't draw. And I believe that this is like the source of a bunch of like really flickery effects that happened on the NES, which is basically, this was a really common technique to sort of like interlacing in frames. You're like literally interlacing your sprites in and out on alternating frames. Yeah, and I guess that gets more, like the flicker period gets like longer depending on how you can shift sprites in and out. But yeah, so those are what I think they are. But maybe we should actually just read the article instead of me sort of speculating about stuff. Okay, so here we have OAM, Object Attribute Memory, Read Write Address. So this is an address where we can read and write to object attribute memory. We'll take a look at that. Object attribute memory data, which is a data read-write. I don't know what the distinction is here. Then we have PPU scroll, which is the fine scroll position. Two writes, X scroll, Y scroll. Not sure what that means exactly, but. And then we have PPU address, read and write. Again, there is some information about multiple writes. PPU data, and then there is object attribute memory, DMA. So DMA is direct memory access, which is basically, in most architectures, DMA is a mechanism that allows you to interact with memory in some way without having to involve the CPU directly, which means you don't have to spend time loading stuff into the CPU and then, shifting it back out. You can actually just bulk shift a bunch of information using this methodology. But it can mean different things, so we'll find out what it means from that. So let's start out with this PPU control. Okay, these are all actually just bookmarks in the same page. So the control register, 2000, it's something we write to. I'm assuming that's what that means. We write to this address. Well, let's read this part. The PPU has an internal data bus that it uses for communication with the CPU. The bus is called _IO_DB in Visual C2, I don't know what that is, and PPU gen latch. It behaves like an 8-bit dynamic latch due to capacitance of very long traces that can run to various parts of the PPU. Writing any value to any PPU port, even the nominally read-only PPU status, will fill this latch. Reading any readable port, PPU status, OAM data, or PPU data, also fills the latch with the bits being read. Reading a nominally write-only register returns the latch's current value, as do the unused bits of PPU status. This value begins to decay after a frame or so, faster once the PPU is warmed up. And it is likely that the values with alternating bit patterns will decay faster. That is, that's just like, yeah, when you come to write an emulator and like you think, oh, it's this digital system, I'm just gonna I'm gonna write to memory here and I'm gonna read from it, and clock cycles take this long, and then you read a piece of information like this, which just tells you like there's some spooky ghost analog effect that happens. And just like this is a source of side effects, like right here. Just who knows, like, oh, I put 55. I've got some bug where if I write 55 for some reason, stuff breaks. That would be such a nightmare to work with. But very interesting. I'm not going to be emulating this physical effect, but we'll see. Maybe some people do. That's getting back to what the comment that I got about, what I called cycle accuracy. Maybe someone talks about PPU accuracy, and then they get this lecture. Okay, so the control register, what it does, its description is PPU control register. We access it by writing to it, and its various flags controlling the PPU's operation. Okay, so this is how the developer tells the PPU what to do. That makes sense. There's something called the base name table address, which takes up 2 bits, which means it represents 4 values. If it's 0, then it represents 2000. If it's 1, then it represents 2400, 2 2800, and 3 2C00. Then we have I, which is the VRAM address increment per CPU read-write of PPU data. 0 is add 1 going across, and 1 is add 32 going down. So this is going to be to do with like thinking about the way things are laid out in memory in a sort of more two-dimensional way. We can think about just scrolling through and incrementing addresses, or we can think about sort of just skipping whole structures. I think this is maybe going to talk about. I'm not exactly sure, but it's definitely going to be something about the way that memory is laid out in a particular way, and that we can sort of think of it being a matrix and addressing it as columns or rows. Sprite pattern table address for 8x8 sprites. If this value is 0, then it's 0, and if it's 1, it's 1000. And this flag is ignored if we're in 8x16 mode. Now 8x16 is what I was talking about with the ability for sprites to be in 2 different positions. The background table address, if it's 0, then it's 0, and if it's 1, then it's 1000. I'm not sure if these are like offsets or if these are like 4 addresses in and of themselves. They're probably 4 addresses. So that's interesting because it basically implies that the 0 table, the 0 page here can be treated as a big table holding things like the background table address. Not exactly sure what that is, but all right. Then we have the sprite size. This controls the mode, and we have the PPU master slave select. So when this is 0, it's a read backdrop from the EXT pins, and when it's a 1, we're going to read an output color from the EXT pins. That's interesting. I'm not sure exactly what that means. I'm not sure what the EXT pins are. I'm assuming that's something to do with the cartridge. Yeah, I think it's about how you... It's the master slave select, read a backdrop. I'm not even sure what a backdrop is, to be honest. Okay, so generate a non-maskable interrupt at the start of the vertical blanking interval. 0 is off and 1 is on. This is now when you go into vertical blank, you know that you can start doing stuff with video memory. So basically what you're doing here is setting up a callback. If you're familiar with like more asynchronous programming in that way, this is basically asynchronous programming. You're getting like an event-driven thing here. So this is basically to enable or disable that. It's possible that you actually don't always want to respond to that, but basically at certain parts of your game logic, you may actually want to respond to that. Okay, so that's pretty interesting. Okay, so equivalently, bits 1 and 0 are the most significant bits of the scrolling coordinates. See name tables and PPU scroll, I will. 1, add 256 to the X scroll position, or 1, add 240 to the Y scroll position. Don't know what that means now, but we'll find out. There's a lot of me saying that I don't know what that means in this video, and I hope that you don't mind that. This is really a journey, like a discovery journey, and I hope that there is some value in just seeing how this actually works, or seeing how that you would approach a project like this. You basically just have to read a lot of documents and try and make sense of them. And you slowly accumulate knowledge about the system, and then you can put that knowledge into practice in the code. So the actual writing of the code is just a much smaller part of the whole thing. It's of course very important, but actually understanding the system is the essence of an emulator project. All right, so another way of seeing the explanation above is that when you reach the end of the name table, you must switch to the next one, hence changing name table address. Maybe it's worth finding out what a name table is before reading more of these things. After power and reset, writes to this register are ignored for about 30,000 cycles. That's interesting. That is something we can emulate, right? I mean, we can put like a 30k wait time for reads and writes in this. It's a I think. Okay, so I think. Wow, it actually goes really into detail on a bunch of this stuff. Okay, so there's also with the slave mode and ext pins. When bit 6 of the Ppu control is clear, which is the usual case, the Ppu gets the palette index for the background color from the ext pins. I wish there was a link here, like what are the ext pins? The stock NES grounds these pins, making palette index 0 the background color as expected. A secondary picture generator connected to the ext pins would be able to replace the background with a different image using colors from the background palette, which could, for example, be used to implement parallax scrolling. Setting bit 6 of the Ppu to output the lower... Setting bit 6 causes the Ppu to output the lower 4 bits of palette memory index on the ext pins for each pixel, in addition to normal image drawing. And since only 4 bits are output, background and sprite pixels can't normally be distinguished this way. As the ext pins are grounded on an unmodified NES, setting bit 6 is discouraged, as it could potentially damage the chip whenever it outputs a non-zero pixel value, due to it effectively shorting voltage and ground together, which, of course, you don't want to do. Looking back at the relevant circuitry in Visual C2COC, so is that like a Visual NES project? I feel I've just completely lost where I was. This link does go to somewhere related to NES Dev. It's a hardware level simulator of the NTSC Ppu by Quietist, using the same core as Visual 6502 project, which I think we very, very briefly looked at in the previous... Oh wow, yeah. Okay, it's not really for now, but it's very cool. So it seems then that for the most part we don't even need to mess around with this whole thing with the ext pins, because it seems that unless you modified the NES, then this stuff is going to be connected to ground, and it's going to have just going to have a particular effect in this way. I love the idea that that you could, as the programmer in your game, you could just write a value to memory and potentially break someone's console. I mean, it's pretty, yeah, so some great power, great responsibility stuff there. All right, and then we'll actually get to the next, the next register. But what I think might be useful to do now is to actually just zip over to the code and start a Ppu class and put some of this logic inside. So start thinking about, also this thing with the 30,000 frame delay, and just some of these names and what they mean and what it means to write these values in or read them. We won't get it all done, but it's something nice to do. All right, so I'm going to make a new file, which will be ppu.header. We'll say pragma once, and we want to make a class for the Ppu, and we're going to have a constructor I'm not holding down shift apparently. Constructor, and we're going to have a destructor at some point. Looks like I've frozen again as well. Maybe this happens at a particular time. I should keep track of that. And then we're going to have some... It's going to put everything on the public at the moment because I don't know what's going to need to be public and private. I mean, very likely all of this internal stuff will be private. But let's put it all here for now. So what I'm actually going to do is I'm going to check individually for those 8. I'm going to check individually for those 8 addresses. And if any of those 8 addresses come up, then I'm going to call, or I'm going to write to a particular instance variable inside. So we're just going to have an instance variable for each of these. So we'll have Ppu Control instance variable. I'm just going to make it all caps, and it's going to be a UN8T. And we're going to have, oh, we need the standard in. Although I think seems that I'm having trouble with it now. No, in any case, we get standard in. We're going to have the PPU mask. Status. OEM address. OEM data. PPU scroll. PPU address. PPU data. And OEM DMA. A nice healthy mix of copy paste and typing and pasting things out. And we also know, well, the one thing I know that we would have as a private variable right now is going to be this 30,000 frame count. So let's give ourselves, what is this going to be? It's going to be like PPU frame delay. And that's going to be, we're going to need to count 30,000, so we're going to need UN16 for that. UN16T frame delay. This should get us by for now. Let's make a PPU CPP file. And we're going to include ppu.header. Should be able to find that. Okay, so can't find standard in, so that's a problem here. All right, we're gonna have, what's this? PPU. And destructor. I am doing constructors and destructors correctly, right? Yeah. Oh, and I've called this .h as well. Maybe I should not do that. And we are going to have something that how would this best be done actually? Because we need to, for instance, do this 30,000 check, and I don't want to leak that information out into the bus because this is the PPU's responsibility. So I think it actually needs its own read and write methods. And I guess we'll just like refer to these like by index. So maybe it would actually make more sense to make maybe it would actually make more sense to do this, to make a uint8 array of the registers. And maybe it would now actually start to make sense to use the membership naming convention. Let's do that. And so we have the M registers, so we don't get confused. There are 1, 2, 3, 4, 5, 6. So I believe there are 8 registers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right, or have I messed this up? Are there actually 9 registers? They can't be, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Huh. OAM DMA is something completely different somewhere else. So it may be part of this, but for now let's leave that out. Which means we're going to have 8 registers, and we're going to just refer to those by these things. So what we can actually do is turn these into defines instead, and we should do that in the header file. We are in the header file, of course. Yeah, so we can define, shift all of those out. Messing around with the keys on my keyboard now. Where am I? Not equals. Let's see. So it's going to be 1, 2, 3, 4, 5, 6, 7. Now we can write in using the names. All right, so then we can have a uint 8t. It might make more sense at some point with the emulator to actually like make these even higher level. I'm not sure yet, but we'll find out. We're going to have a read, and that's just going to be yeah, we'll make that uint8t register index, and we're going to have a write, which will take a register index and a uint8t value, and write will not return anything. Okay, so we're going to implement these. Trying to like do keyboard stuff in gloves. It's not quite as easy as it might seem to be. All right, so basically in read, we're just going to read something out of our, what do they call it? Let's put this here on the left and drag that out. Maybe I'll put myself down here for now. I don't know why this thing doesn't disappear sometimes, but it just does its own thing. All right, so what we want to do is we want to return from our M registers using the register index. But yeah, of course, this can like easily like not be in range, so we'll end it with OX. And it with, what do we need here? We need just to, maybe it's better just do this in like binary, 1, 1, 1. yeah, so we just basically, like, we're going to take whatever's in the bottom 3 bits. So if they give us a register which is like higher than that, like, we'll still read something valid. I mean, it'll be weird and we'll get a weird bug from that, but it's better than like crashing unnecessarily. And then in terms of writing, we want to just do the same thing again. Actually, we don't quite want to do the same thing again because there's going to be like specific. There's going to be a specific thing. So actually, probably more what we're going to do in here is have a switch statement, which is going to look at the register index and 0B111, and we're going to do some stuff based on that. Yeah, and now we can actually do this 30,000 thing. So we've got this PPU frame delay. So when the thing sets up, we're going to set that up and PPU frame delay. Set that to 0. And oh, that's interesting. Yeah, of course we don't actually know the number of frames yet, so we will know that from here at some point, but we don't know it right now. Let's maybe make a UN32. Is UN32 going to be enough? Or why not make it a UN64? Just to make sure. And that will be M frames elapsed. So we're just going to increment that every frame by whatever mechanism we end up with, how frames get drawn. And like for every read or write, yeah, see, the read is interesting because the read is going to be this weird undefined analog behavior thing that happens. When you read, you're going to be reading this latch, and there's going to be, yeah, basically it doesn't work properly at that point. So I'm not sure if there's a specific thing that happens, but what I'm going to do is return 0 in those cases, or return in the case of write. So what we're going to do is we're going to say if M frame... Actually, we don't need frame delay, right? If we're keeping track of the number of frames that have elapsed in general, we don't need a frame delay variable. We just need to check if the number of frames elapsed is greater than or equal to 30,000. Let's just make a define here, which is going to be like the PPU frame wait time. And for now, we'll put that 30,000. And we'll change that later if we find out that there's like a more exact number or if there's a better thing. Just return 0. And let's actually put it up on one line. And if it happens at this point, then it's a void function, so it doesn't really matter. We're just going to return. Yeah, cool. So that's the skeleton. We've emulated this weird 30,000 thing. We're not doing anything in particular with the register reads or writes right now. Yeah, but basically we could write into this register. We can... What do we have? Where's the next one? This is also a write register, so we can write into this. Well, like for all of these different things, code-wise, like for all of these different like bit values and things like that, we're just going to make defines that refer to like those bit positions, and we're going to be able to talk about them at a slightly higher level, and I might even make some abstractions for reading and writing to exact bits or yeah, whatever we need to do with that. Yeah, cool. Let's call it a day here for now. We haven't written that much code, but I hope you feel that you've come away learning more about the system. I hope you've enjoyed it. Thanks for watching, and I'll see you next time.